A shipwreck's cargo holds secrets to a journey spanning oceans. We can now track a single ancient shipment across continents using 22 hidden clues. By the end of this video, you will understand how scientists rebuild entire trade routes from microscopic evidence. How can a fleck of pollen or a metal's chemical signature map a voyage lost for millennia? What forgotten story does a simple piece of pottery truly tell? Every object tells a story if you know how to read it. This is the core idea of provenance, the biography of an item that traces its life from creation to final resting place. Think of it not as a static relic, but as a silent witness to a journey. For a single ship's cargo, establishing provenance is the ultimate act of historical reconstruction. It transforms a scattered collection of pottery and metal into a coherent narrative of ancient commerce and human connection. As leading scholars like Professor Michael McCormick of Harvard University point out, the movement of goods is fundamentally the movement of people and their ideas. A simple clay jar is more than just a container. It is a carrier of chemical, geological, and even cultural information. This foundational principle is the bedrock of our entire quest. It sets the stage for the incredible scientific detective work that follows, where we bridge vast distances and millennia through the silent testimony of materials themselves. With this understanding, we can begin our detailed examination of the specific clues that make such precise tracing possible. Deep within a bronze ingot cast over 3,000 years ago lies a secret passport. This is not a document of paper, but a record written in the language of atomic decay. The metal holds a precise ratio of lead isotopes, a unique signature inherited directly from the ancient ore deposit it was smelted from. Think of an isotope as a version of an element with a slightly different weight. The specific mix of these lead isotopes in a copper or tin ingot is like a chemical fingerprint, one that is virtually impossible to fake and entirely unique to its geological birthplace. Whether the ore was ripped from the famed Lavrian mines in Greece or the rugged Taurus mountains of Turkey, it carried this distinct identity with it. When archaeologists today analyze these ratios using a machine called a mass spectrometer, they can pinpoint the origin of the metal with astonishing accuracy. This geochemical clue is our first and most powerful link, providing a near-definitive starting point on our map. It tells us without question where the journey of this specific piece of cargo began. But knowing where it started is only half the story. The true challenge lies in reconstructing the entire path it took. Yet that lead isotope fingerprint, as definitive as it is, tells only one part of the metal story. To truly understand its origins, we must listen to a second, quieter voice whispering from within the ingot. This voice belongs to the trace elements, the accidental impurities that snuck into the metal during its creation. While the lead isotopes point to a specific mine, these trace elements like arsenic, nickel, or silver tell us about the smelting process itself. They are the unintended ingredients in the ancient metallurgist's recipe, a recipe that varied from one workshop to the next. For example, a distinctively high level of cobalt locked within the copper might be a telltale sign of ores from Central Europe. Conversely, an elevated amount of antimony could point directly to a smelting site in ancient Anatolia, modern-day Turkey. These impurities are not flaws, they are a secondary signature, a confirming piece of evidence that enriches our understanding. They speak of the local geology and the unique technological choices made by the smelters, adding a compelling layer of human activity to the cold, hard data of the isotope map. Together, these two chemical clues build an almost undeniable case for where the metal was born. But this is just the beginning of the cargo's journey. Once the ingot was cast and marked with its invisible chemical passport, it was ready to travel, and its next stop would leave a completely different kind of clue. But the story of the metal does not end with its chemical composition. If we peer even deeper into the microscopic realm where the metal's own internal architecture resides, we uncover a third powerful clue. This evidence is written in the language of crystals. When a molten ingot cools and solidifies, it forms a unique internal landscape of microscopic grains. The size, shape, and arrangement of these metallic crystals are a direct result of the human actions taken upon it. A piece that was cooled quickly after casting will be filled with a chaotic jumble of tiny, fine grains. Conversely, an ingot that was intentionally reheated and cooled slowly, a process called annealing, will display large, uniform, and orderly crystals. Furthermore, if that metal was later hammered or shaped by a craftsperson, the crystals would be stretched and deformed, leaving a permanent record of that physical labor. This microstructural crystallography is like reading the ingot's personal diary of manufacture. By comparing these crystalline fingerprints across a cargo, archaeologists can perform a kind of forensic match. If multiple ingots share an identical internal grain pattern, it strongly suggests they were not just from the same mine, but were likely cast in the very same workshop, following the exact same technical recipe. This clue moves us beyond the geology of the source and directly onto the workshop floor, letting us almost see the ancient metalworkers making deliberate choices about how to prepare their valuable commodity for its long journey. Yet, once this ingot left the smith's hands, its voyage was only beginning, and its next companion would be something far more humble, yet equally telling: a simple clay pot. While the metal ingot carries its story in chemistry and crystal, the humble clay pot speaks with the very voice of the earth itself. Every ancient potter knew that pure, fine clay was a recipe for disaster in the kiln. To prevent their creations from cracking or warping as they dried and fired, they would mix in a coarse material called a temper. This was not a standardized ingredient, but a practical solution using whatever was locally abundant. One workshop might crush up old, broken pottery into what is known as grog. Another, living near a coast, would mix in finely ground seashells. A third, situated in a volcanic landscape, would use gritty sand rich in specific minerals. This temper is the pot's hidden anchor to its homeland. When a thin slice of a pottery sherd is placed under a powerful microscope, a whole new world opens up. A technique called petrographic analysis allows scientists to identify the exact mineral crystals trapped within the clay fabric. It is like examining the geological fingerprint of the potter's own backyard. For instance, a temper laden with distinct grains of volcanic feldspar and a greenish mineral called pyrozine acts as a direct geochemical signature. This combination could point unequivocally to a workshop located on one of the Aegean islands, whose soils are born from ancient volcanic activity. Conversely, a temper made of crushed limestone would tell a completely different story, one of a workshop built upon a bedrock of chalky sediment. This clue, the mineralogical composition of the temper, does more than just tell us how the pot was made. It gives the vessel a verifiable geological address, tethering it irrevocably to the specific patch of ground where the potter gathered their materials and practiced their craft. But the journey of this pot was just beginning, and its surface holds another, more visible clue waiting to be read. Sometimes the most telling clues are not minerals, but the ghosts of ancient life. Beyond the gritty sand or crushed shell, a pot's temper can preserve a microscopic fossil record. These are the imprints of tiny, single-celled organisms called foraminifera, or the delicate glassy skeletons of diatoms. Each species of these microscopic creatures lived in a very specific environment at a very specific time in Earth's deep past. When a potter dug their clay from a pit that cut through an ancient fossil bed, they unknowingly mixed a biological timestamp into their work. Finding a particular species of foraminifera in a potsherd is like uncovering a tiny, fossilized address label. For example, if the microfossils trapped in the clay are from a species that only thrived in the shallow sea that once covered coastal Cyprus, it places the pot's creation on that island with startling precision. This biological fingerprint works in perfect harmony with the mineral one. The minerals tell us the general geological province, while the specific microfossils can point to the very quarry or clay bed. It is a dual-layered verification, a one-two punch of geological and biological evidence that makes the pot's origin almost undeniable. This humble container, now holding the echoes of a primordial sea, was ready for its journey. But before it could be loaded onto a ship, it had to be filled, and that act would leave its own distinct mark upon history. The shape of a pot is a deliberate cultural statement. While its mineral temper and hidden fossils anchor it to a specific geology, its physical form speaks the language of its makers. Archaeologists call this stylistic typology, and it is the art of reading a vessel's cultural identity from its silhouette. Every curve, from the distinctive flair of a rim to the elegant arc of a handle, was a conscious choice reflecting deep-seated local traditions and practical needs. For example, a tall, slender amphora with a pointed base, often called a carrot-shaped amphora, is an almost unmistakable signature of the island of Rhodes. Its design was perfected for stability in a ship's hold and easy transport over land. Just a few miles away, a workshop in Knidos might produce a bulbous, round-bodied amphora with a completely different profile. By meticulously documenting these profiles, the types of handles, and the forms of the bases across a ship's cargo, specialists can perform a kind of cultural triage. This analysis connects the object not just to a place on a map, but to a specific community of people, their aesthetic preferences, and their solutions to everyday problems. It provides a human context that pure material science cannot capture, telling us not only where the pot was made, but who made it and for what purpose. Yet, even this clear cultural signature can be deliberately copied or misunderstood, which is why the next clue looks past the pot's elegant shape to the very marks left by the hands that formed it. The final touch on a pot's surface can be as revealing as its hidden temper. Before a vessel ever saw the inside of a kiln, a potter might coat it with a fine slurry of liquid clay, known as a slip. This was not merely for decoration. A slip could change the pot's color, make it less porous, and in the hands of a master, become the canvas for intricate artwork. The chemistry of this surface layer is a deliberate recipe, as unique to a region as its clay beds. Take the world-renowned black figure pottery from ancient Athens. Its dramatic, dark figures were not painted with a dye, but achieved through a sophisticated dance of chemistry and fire. The potters used a slip made from an exceptionally iron-rich local clay. When fired in a kiln where the oxygen supply was carefully cut off, a process called a reducing atmosphere, that iron-rich slip would transform into a deep, lustrous black. This specific technical choice, using that particular Attic clay for the slip, is a verifiable signature. Scientists can now take a portable X-ray fluorescence analyzer, a device that looks like a sci-fi scanner, and gently place it against the pot's surface. Without causing any damage, it reads the elemental composition of that black glaze. The machine might detect a telltale ratio of iron to other elements that screams Athenian origin. A different slip, rich in manganese perhaps, could point directly to a workshop in Corinth. This analysis of the surface treatment adds a powerful, final layer of confirmation. It connects the object not just to a geological source, but to the very artistic tradition and technological knowledge of a specific city-state. The pot now carries the invisible signature of its clay, its temper, and its final finish. But after the kiln cooled, this finished pot was still just an empty container. Its true purpose and its next great clue would only emerge when it was filled. The mud clinging to a ship's hull holds more secrets than you might think. Harbors are not just waypoints, they are living archives, patiently collecting the dust of centuries. Year after year, they accumulate layers of sediment, each one a timestamp of its era. Scientists call this layered sequence stratigraphy, and reading it is like turning the pages of a history book written in dirt and sand. To access this archive, researchers use a hollow tube to extract long, vertical cores from the bottom of ancient harbor basins. Pulled up from the depths, these cores reveal a stunning visual timeline. A dark band of charcoal might speak of a devastating city fire. A fine layer of volcanic ash, its chemical signature unmistakable, could be the fallout from a specific, long-forgotten eruption. The precise order and composition of these layers create a unique geological barcode for each and every port. Now, imagine a shipwreck is discovered. Its wooden hull, preserved for millennia, is coated in a thick layer of hardened silt. When scientists analyze that specific mud, comparing its mineralogy, its microfossil content, and its very sequence of layers to the master cores taken from known harbors, they can find a match. If the silt on the wreck aligns perfectly with the stratigraphic fingerprint of, say, the ancient port of Carthage, it places that ship directly in those waters at a specific moment in the harbor's history. This clue transforms simple mud into a powerful historical calendar, placing the vessel at a concrete point on its final journey. But the harbor silt is a snapshot of a single stop, a moment frozen in the ship's logbook. To understand the full route, we need a clue that captures the entire voyage, a record of the changing seas and skies the ship sailed through. The very mud that caked a ship's hull holds a botanical secret, a ghostly echo of the ancient world. Locked within those harbor silts are countless pollen grains and spores, each one a tiny, nearly indestructible capsule of genetic memory. These are not just specks of dust, they are the airborne legacy of the landscape that surrounded the port. When rainwater washed over the hills and fields near the harbor, it carried this invisible rain of plant life into the water, where it settled into the mud layer by layer, year after year. Scientists who specialize in this field, called palynology, can extract these ancient grains and identify the plants they came from. This allows them to reconstruct the entire ecosystem that once thrived there. Imagine analyzing a silt sample from a ship's anchor and finding it saturated with the pollen of olive trees. This would be a powerful indicator that the ship had last anchored in a region like coastal Greece or Lebanon, where olive cultivation was a cornerstone of the economy and the landscape. Conversely, a sample filled with the spores of hardy desert weeds and drought-resistant shrubs would point the finger toward a port in a more arid climate, perhaps on the North African coast. This palynological profile becomes a unique environmental fingerprint for each harbor. By matching the specific mix of pollen and spores found clinging to a cargo's pottery or metal ingots to the known botanical record of a candidate port, researchers can confirm a stopover with remarkable confidence. It is a clue that uses the silent, ancient language of flowers and trees to tell us exactly what the world looked like when that ship last dropped its anchor, waiting to continue its voyage across the known world. Even the air of an ancient port was thick with the residue of human industry. The 10th clue lies in these microscopic flecks of soot, coal, and ground pigments that settled into the harbor mud. This is ancient microplastic, a cloud of anthropogenic particles unique to each city's industrial heartbeat. A harbor servicing metal workshops would rain down a fine dust rich in copper and lead residues. A port known for its dye-making vats might leave a persistent signature of crushed murex shells or the vibrant chemical traces of rare pigments like Egyptian blue. When the wind blew and the rains fell, this unique cocktail of industrial waste would wash into the water, settling into the silt layers as a permanent, invisible record. Finding this specific blend of particles coating a ship's cargo is like finding a tiny, preserved sample of the port's atmosphere. If a set of amphorae and bronze ingots from the same wreck all carry an identical mix of coal dust from forges and a rare red ochre pigment, it points overwhelmingly to a single common exposure. They all sat together in a harbor where those industries thrived side by side, breathing in the same industrial air. This clue connects the objects not just to a geographical location, but to the very economic engine of a port city, tying their journey to the bustling, smoky reality of ancient trade and production. It is a ghostly echo of the city's daily life, captured on the surface of artifacts that waited patiently for their voyage to resume. The very wood of the ship's hull holds a secret calendar. Deep within the grain of every timber, crate, or piece of dunnage is an unalterable record of time itself, a story written in rings. This is the power of dendrochronology, the science of tree ring dating. Trees do not grow at a constant rate. In a good year with ample rain and sun, they add a wide, generous ring. In a year of drought or cold, they lay down only a thin, tight line. This alternating sequence of fat and skinny rings is unique for every era and region, creating a pattern as identifiable as a fingerprint. Scientists have spent decades building master chronologies for specific tree species like oak or pine across the ancient world. These are like library reference books for time, stretching back thousands of years. When a piece of wood from a shipwreck is recovered, a specialist will take a core sample, carefully sand it until the rings are perfectly clear, and then align its pattern against these master charts. The moment the sequences lock into place is a moment of pure revelation. It tells them the exact year the tree stopped growing, the precise date it was felled by an ancient woodsman. Imagine a ship whose whole planking is made of oak that was cut in a forest in southern France in the year 125 before the Common Era. That single piece of data does more than just date the ship. It anchors the entire vessel and its cargo to a specific shipyard at a specific moment in history. It gives us a verifiable starting line for our entire investigation, a fixed point from which every other clue can be measured. This wooden timestamp is our 11th clue, a foundational pillar that transforms a collection of objects into a story with a known beginning. But a ship's journey is defined by its destination as much as its origin, and for that we must look to the cargo that never made it to port. The silent geometry of a shipwreck tells its own story. When the seafloor preserves the final resting place of a cargo, it captures a frozen moment of ancient logistics. This 12th clue is not in the objects themselves, but in their precise arrangement. How amphorae were stacked in the hold, their necks pointed inward for stability, the specific use of brushwood or straw as dunnage to cushion them, even the order in which different goods were loaded. All of this leaves a distinct archaeological pattern. These are the fingerprints of the stevedores, the dockworkers who mastered the art of packing a ship for a long and perilous voyage. Imagine discovering a wreck where a layer of wine amphorae from Italy is always stowed directly beneath a layer of fine tableware from Greece, with a specific type of dried grass from a North African riverbed woven between them as padding. This recurring, almost ritualistic stowage pattern is not a coincidence. It points to a highly organized commercial practice, a routine perfected at a specific operational hub. A port like ancient Alexandria or Piraeus would have developed its own loading efficiencies, a signature way of maximizing space and minimizing breakage that became second nature to its workforce. Finding this pattern across multiple shipwrecks is like recognizing the handwriting of a major trading company. It connects a cargo not to a mine or a clay bed, but to a commercial network's beating heart, revealing the unseen human routines that kept goods flowing across the Mediterranean. But after the ship was loaded and its manifest finalized, the final, most human clues were added, marks of ownership that would speak across the centuries. A simple stamp pressed into the wet clay of an amphora can be worth more than the wine it once held. This is our 13th clue, the most direct message sent to us from the ancient world. Before a pot was ever fired, it was often marked with an official seal, a stamp bearing the name of the producer, the estate owner, or even the local magistrate overseeing trade. These are not random marks, they are bureaucratic signatures, a form of ancient branding and quality control. Then there is the graffiti, the informal scratching added after firing. A dockworker might carve a number denoting its price, or a merchant could scratch a symbol to claim ownership of the entire batch. These inscriptions transform an anonymous piece of pottery into a documented commodity with a known provenance. For example, finding a stamp that clearly reads the letters SES could be instantly recognizable to specialists as the mark of a prominent estate on the island of Samos. It is a literal name tag, a piece of the puzzle that requires no complex chemical analysis to interpret. This epigraphic evidence provides the most human connection possible, naming names and places directly. It ties the object to a specific person, a specific business, and a specific moment within the bustling, paperwork-driven reality of the ancient economy. Yet, even these clear labels only tell us where the pot came from and who owned it, not the intricate path it traveled to reach its final, sunken resting place. The silent interiors of these ancient jars hold their most intimate secret. After the clay was fired and the stamps were pressed, these containers were filled with the very lifeblood of the ancient economy. We can now listen to these whispers using a remarkable scientific technique called gas chromatography mass spectrometry. This process acts like a molecular detective, vaporizing a tiny sample from the inside of a pot and separating its chemical components to identify even the faintest traces of what was stored there thousands of years ago. The presence of a specific compound called tartaric acid, for instance, is the undeniable chemical fingerprint of wine, but the analysis goes even deeper. The unique blend of fatty acids and lipids left behind by olive oil can sometimes point to the specific variety of olive used or the region where the trees were cultivated. Finding that a whole cargo of amphorae all carry the same chemically identical resin-coated wine tells a powerful story. It confirms that this was not a random assortment of goods, but a single, homogeneous shipment, a bulk order of a specific product from a specific source. This residue analysis transforms an empty pot into a testament of ancient taste and commerce. It tells us not just that they traded wine, but the very vintage and style that was in demand, adding a rich layer of economic and cultural meaning to the physical journey of the ship. The cargo itself is only one part of the sunken story. Scattered amongst the grand amphorae and heavy ingots are the small, forgotten items of daily life, the personal possessions of the crew who lived and worked aboard the vessel. A single bronze coin minted in Syracuse, a humble oil lamp crafted in the distinctive shape popular in Ephesus, a carved gaming piece made from a local bone or wood. these are the 15th clue. These associated small finds are the human breadcrumbs left behind on a vast commercial journey. They tell a story of people, not just products. A coin from Carthage, found tucked between the planks of a ship whose main cargo is Greek wine amphorae, speaks volumes. It suggests a multi-leg voyage where the ship called at ports under different political control, or perhaps it hints at a culturally mixed crew, a microcosm of the interconnected ancient world. A sailor might have been paid in a foreign currency at one port, only to lose it at sea days later. A distinctive lamp could have been a personal purchase, a souvenir from a previous journey, or standard issue from the ship's home port. When analyzed together, these personal artifacts build a rich profile of the people behind the trade. They indicate probable ports of call beyond the major hubs, suggest the nationalities or origins of the sailors, and illuminate the quiet cultural intersections that happened every day on the decks of these ancient freighters. This clue paints the final, most intimate layer onto our map, transforming a sterile trade route into a human journey, reminding us that every sunken cargo was once a floating world with its own stories, its own losses, and its own small, personal treasures. The stones that kept a ship steady on the high seas hold a secret of their own. Every vessel needed ballast, heavy material stacked low in the hull to provide stability against the unpredictable ocean. This was not a manufactured good, but a simple, practical necessity. Crews would typically gather these stones right at or near their port of departure, simply because it was the easiest and cheapest solution. The geological type of these ballast stones, their lithology, becomes a powerful, if humble, clue. A ship laden with smooth, water-worn granite cobbles likely took on its ballast in a region where granite bedrock is the foundation of the landscape. But the clue becomes even more precise with distinctive stone. Imagine ballast stones made of a porous, lightweight volcanic tuff with a unique greenish hue. This specific mineralogy could act as a direct geological signature, pointing unequivocally to a volcanic island like Thera or Melos, whose very earth is composed of such materials. By carefully cataloging and analyzing the ballast stones recovered from a wreck, geologists can essentially work backward. They match the stones to known outcrops and quarries across the Mediterranean, inferring the geological setting of the ship's home port or a major port where it was loaded. It is a beautifully straightforward piece of evidence, using the literal foundation of the ship's voyage, the weight that kept it upright, to whisper the name of its starting point. This simple, often overlooked pile of rocks completes our picture of the journey's origin, but it also sets the stage for the final, most dramatic phase of our investigation, the moment the voyage ended and the story was frozen in time. The wood of the ship's hull carried a living map in its very fibers. Below the waterline, the submerged timbers offered a home to specialized marine mollusks known as shipworms. These are not true worms, but a type of clam that has evolved a long, soft body and a small, jagged shell it uses to rasp and burrow deep into wood. The species that colonized a vessel were not random. Each one thrives within a specific range of water temperature and salinity. The telltale burrows they leave behind are a permanent record of their presence. When archaeologists examine these labyrinthine tunnels under a microscope, they can identify the exact species of shipworm that created them. Finding the fossilized remnants of a species called Bankia carinata, for instance, would be a powerful indicator. This particular mollusk is almost exclusively found in the warm, tropical waters of the Indian Ocean. Its burrows etched into the hull planking would be a clear biological signature that this ship had sailed through those southern seas. Conversely, the presence of a different species, like Teredo nivalis, which prefers the more temperate conditions of the Mediterranean, would point the narrative in a completely different direction. This field, known as Paleo-Parasitology, allows us to read the ship's travelogue not from a logbook, but from the climatic preferences of the stowaways it carried on its skin. It reveals the general environmental conditions of the journey, telling us whether the vessel was a coaster of familiar, cooler waters or a deep-sea voyager that braved the warm, equatorial currents. This living clue, written by nature itself, adds a profound layer to our understanding, charting the vessel's path across the very climates of the ancient world. Even the ropes that held the cargo fast whisper of distant landscapes. The fibers used for cordage, sailcloth, and protective wrappings carry their own botanical identity, a clue often overlooked because such organic materials so rarely survive. Yet when a fragment of rope or a scrap of woven fabric is preserved in the anaerobic mud of a shipwreck, it opens a window onto the agricultural world of the ancient port. Under a microscope, the cellular structure of a plant fiber is as distinctive as a fingerprint. Flax, which would be woven into linen sailcloth, displays long, smooth filaments. Hemp fibers are coarser and more robust, ideal for heavy-duty anchor lines. Then there is esparto grass, a tough, wiry grass native to the arid landscapes of Spain and North Africa. Finding esparto grass cordage bundled around a set of amphorae is like finding a shipping label that reads, "Packed in the Western Mediterranean." This is not just about the material itself, but about the economic and environmental logic of the ancient world. A shipwright in Carthage would not import expensive hemp from the Aegean when a durable, locally abundant grass like esparto was readily at hand. The very choice of fiber speaks to a culture's immediate environment and its practical wisdom. Furthermore, the weave pattern of a surviving piece of sailcloth, the specific way the threads are interlaced, can be culturally indicative, a traditional technique passed down through generations of sailors in a specific region. This analysis of perishables adds a crucial, tactile thread to our evidence. It tells us not just where the ship was going with its goods, but where it was last equipped and repaired, grounding the vessel's story in the very plants that grew on the shoreline it once called home. The black, sticky tar used to seal a ship's seams holds the scent of an ancient forest. This 19th clue lies in the waterproofing materials themselves, the pitch and tar that kept the vessel seaworthy and its precious cargo dry. Mariners produced these vital sealants by distilling the resin of pine trees, a technology as old as seafaring, but the chemical signature of the resulting tar is not universal. It changes depending on the specific species of pine tree that was tapped and the unique methods a particular community used to cook the resin. Scientists can analyze these tars using a technique called biomarker analysis, which identifies the distinct organic compounds locked within. This allows them to match a sample to known production centers. For instance, the thick, high-quality pitch from the pine forests of Calabria in southern Italy had a reputation across the ancient world. Its chemical fingerprint is so distinctive it acts like a label. When archaeologists find that same Calabrian tar used to coat the ship's hull planking and also sealing the stoppers of a cargo of wine amphorae, it tells a powerful, unified story. It means the ship's last major maintenance, the caulking of its seams, and the preparation of its goods all happened at a port with access to that specific Italian pitch. This clue moves beyond the cargo and into the realm of the ship's own upkeep, pointing directly to the harbor where it was made ready, its hull freshly tarred for the long and dangerous voyage ahead. The lead armor protecting the ship's hull carries a story all its own. While the cargo below deck speaks of its final commercial mission, the very skin of the vessel records a longer, more personal history of maintenance and repair. Some Roman ships were sheathed below the waterline with sheets of lead, a brilliant defense against the relentless burrowing of shipworms and the slow decay of wood. Just like the bronze ingots in the hold, this lead sheathing possesses its own unique isotopic fingerprint, a geochemical passport pointing directly to the mine where its ore was born. Now consider the profound implication when these two stories diverge. Imagine a wreck where the cargo of wine amphorae, with their mineral tempers and resin residues, points unmistakably to the eastern Mediterranean. Yet the lead sheets nailed to the hull trace back to the distant, misty mines of Roman Britain. This is not a contradiction, it is a revelation. It tells us that the ship's life was longer and more complex than its final voyage. Perhaps this vessel, originally built in the warm waters of Greece or Italy, decades later sailed into a port in Gaul or Hispania, its original sheathing worn and torn. There, in a foreign shipyard, workers stripped the old lead and hammered on fresh sheets sourced from the Atlantic provinces of the empire. This single clue, the sheathing, opens a parallel narrative. It chronicles the ship's own arduous career, its repairs in far-flung ports, and the vast, integrated network of raw materials that kept the empire's lifeblood flowing. The cargo tells us where the ship was going, but its leaden skin whispers of all the places it had been. The very density of a clay pot speaks volumes about the hands that fired it. We return now to the ceramic vessel, but instead of looking at its shape or its surface, we peer into its soul, into the microscopic world of its hardened fabric. This 21st clue is porosity. It is the measure of how much empty space exists between the fused particles of clay, and it is a direct result of the heat it endured inside the kiln. A pot fired at a consistently high temperature, perhaps 1,100 degrees Celsius or more, undergoes a process called vitrification. The clay particles begin to melt and fuse together, creating a dense, almost glass-like, non-porous body. Achieving this requires a sophisticated, well-insulated kiln, the kind typically found in a major industrial production center like ancient Athens or Corinth. These were the advanced workshops of their day, capable of controlling their fire with precision. Now contrast that with a shard that is softer, more crumbly, and visibly porous. This lower fired fabric, perhaps only reaching 700 or 800 degrees, tells a different story. It suggests a simpler, less controlled kiln, maybe a single-chamber pit kiln used by a rural workshop supplying a local market. The potter here had less command over the inferno, resulting in a vessel that was more porous and less durable. This simple physical test, measuring how much water a dry sherd absorbs, does more than just assess quality. It provides a clear window into the technological landscape of the ancient world. It tells us whether our pot came from a bustling industrial hub with master craftsmen, or a quiet village kiln operated by a local artisan. This final characteristic of the pot itself, its very density, completes the story told by its shape, its temper, and its surface. It is the last whisper from the workshop, a quiet testament to the level of fire and skill that brought it into being, ready to carry its contents across the sea. The final clue emerges not from a single object, but from the entire collection speaking in unison. Each shipwreck carries a unique personality, a distinct signature defined by the specific combination of goods it was carrying. This is the power of the comparative cargo assemblage, where the whole becomes far greater than the sum of its parts. By taking the complete inventory of a wreck, the mix of pottery forms, the types of metal, and even the personal items, and comparing it to the inventories of other known shipwrecks and to goods found in terrestrial settlements, archaeologists can spot a recurring pattern. Imagine a specific, almost ritualistic combination of goods that keeps appearing together. One shipwreck might contain a cargo of carrot-shaped Rhodian wine amphorae, a hold filled with copper ingots bearing the distinct trace element signature of Cyprus, and a small, precious consignment of black figure drinking cups from the workshops of Attica. Finding this exact same combination of objects from these same specific sources on multiple shipwrecks scattered along a sea lane is not a coincidence. It is the undeniable fingerprint of a major, well-established trade route. This holistic approach is the ultimate synthesis. It takes the 21 individual clues from the lead isotopes in the metal to the pollen in the harbor silt and weaves them into a single, unshakable narrative. It confirms not just the origin and stops along the way, but the very nature of the trade being conducted, revealing the complex, interconnected economic systems that bound the ancient world together. So we have 22 separate pieces of evidence, each a whisper from the past, but a whisper alone is easy to dismiss. The true revolution in understanding comes when these whispers begin to speak in unison, when they form a chorus that tells one undeniable story. This is the power of synthesis, the careful weaving of all these independent clues into a single, unbreakable narrative. Think of it like a courtroom case. A single fingerprint at a scene is compelling, but it is not enough. Combine it with a matching fiber, a credible eyewitness, and a clear motive, and you build an argument that is virtually impossible to refute. Modern archaeology operates on this exact same principle of multi-proxy verification. The lead isotopes in a bronze ingot might scream Cyprus. That is our first witness. The mineral temper in the accompanying amphorae, loaded with volcanic minerals unique to the Troodos Mountains of Cyprus, confirms it. That is our second, independent witness. Then we analyze the microscopic harbor silt still clinging to those same amphorae, finding a specific stratigraphic layer and a mix of pollen that matches a core sample from the port of Alexandria. Our third witness places the ship at that specific Egyptian harbor. When these three separate, scientifically distinct lines of inquiry all point to the same sequence of events, we have moved far beyond speculation. We have built a timeline. We can now state with confidence that this ship took on copper from Cypriot mines, was loaded with pots made from local Cypriot clay, and then sailed to Alexandria, where it sat in the harbor before its final, fateful voyage. This converged evidence transforms a scattered pile of artifacts into a detailed itinerary, a map of not just physical travel, but of cultural and economic exchange. It allows us to trace the entire life of a single cargo, from the moment the ore was smelted and the pot was thrown, to its final resting place on the seafloor, giving us a breathtakingly intimate window into the daily rhythm of the ancient world. These 22 clues transform a sunken wreck from a pile of artifacts into a living network. It was never just a ship carrying goods. It was a floating hub of human connection, its voyage a thread woven into the vast tapestry of ancient globalization. Every bronze ingot with its geochemical passport, every clay pot whispering of its local soil, every fleck of pollen from a distant port, all of these pieces come together to rewrite our maps. They reveal trade routes with the precision of a modern shipping manifest, proving that the ancient world was far more interconnected than we ever dared to dream. This detective work does more than track objects, it resurrects the people behind them. It lets us glimpse the merchant calculating his profit, the sailor mending a sail, the potter kneading local clay. Their individual stories, once lost to the deep, are now being heard again. I invite you to carry this detective's eye into your own world. Look at the objects on your shelf, the materials in your home. Each one has a hidden journey, a story of its own passage across the globe. Which of these 22 clues did you find the most fascinating? Was it the silent calendar of tree rings or the ghostly pollen trapped in the mud? Let me know your thoughts in the comments, and if you enjoyed this journey into the deep past, subscribe to join us as we continue to unravel history's greatest mysteries.